do things like that. Now, for many cases, say for a lot of web companies, you want to take a data center full of devices, but want to ask, what can I do for a data center full of memory? So Memcached is a standard way to work with distributed memory when you have a data warehouse full of memory. And you could do things like grep, or you could do UDFs, you could do whatever you want, including quasi-SQL stuff. So I'm going to talk a little bit about stacks for big data, the software infrastructure. This is really of interest for those of you who are interested not in applications, but in actually designing your stacks. On the other hand, I'm going to try to give a perspective to those people building applications. So the good news is, if I have big data these days, there are hundreds and hundreds of stacks that you can try. The bad news is most of them don't work. Most of them won't be around in a few years. And the only information about many of them is blogs. And I've been surprised to find that not everything you read in a blog is authoritative, and not everything you read in a blog makes sense. So it can be a little hard to sort of sort out there with all these choices and all these blogs telling you about what works and what doesn't. Just to remind you of the history, because it's about a decade now. This started almost 10 years ago when Google decided that they weren't going to use the then current way that existed in HPC to work with their internet scale data. They created a file system that scaled to a data center. Over the files, that was called Google File System, as you know, and they, for whatever reasons that will remain forever obscure, they published a technical report about that in 2003. Then they described their MapReduce framework, which is what I just described to you in 2004, and then a NoSQL database called Bigtable that gave you column-based operations in 2006. I've already described MapReduce, so I'm not going to describe it again. In each chairs that have full disk, you pull out the words. That's the map. This is the word count version of that. Then I do a pull, and I pull from all the buckets on each of the local disks and by the key, and then I do some operation on the key. Concatenate web pages for an inverted index, or count for word count. So here's a picture. This is how I think of MapReduce. You got all these disks, you got all these arrows, and you define the map, you define the reduce. But it scales to a warehouse. What that means is, in a warehouse, in an HPC, we pay a lot of money. If you think about the blue gene, we pay a lot of money so it slants. We pay a lot of money so it has a nice black sheen. We pay a lot of money so it has a proprietary interconnect. We pay a lot of money so it's reliable. In a warehouse, if you've ever been in a warehouse, you have to think of the warehouse as full of very unreliable components that are always breaking. So at any given time, a non-significant fraction of the warehouse is broken. And so what that means is the role of your software is to identify the broken pieces, to restart the reroute the computation so it doesn't use the broken pieces, to restart as necessary those tasks that have to be restarted because there's a broken piece. And in some sense, big data in warehouses is about building reliable software that works reliably over components that are unreliable. So all the hard work Gu has done is really to scale. Means you figure out how to work with unreliable components by building reliability into the software and assuming that the hardware is unreliable. The other alternative is to spend a lot of money and get reliable hardware. So here's a picture of the stack. There's a file system, there's the Bigtable, there's the MapReduce, and then there are apps. So MapReduce is a Google file system app. Bigtable is a Google file system app, etc. And so everything is based upon the file system and then using that to scale up. And then the apps are based on the performance of MapReduce. What people don't sometimes realize is you don't have to do things in MapReduce. You could do whatever you want over Google file system. Now, that's, of course, if you're at Google. If you're not at Google, then you use Hadoop. So, you know, even though you may think you're required, you know, when you sign up for your stipend as a grad student, you know, you may think there's a statement in there you have to use MapReduce. It turns out that you can use whatever you want. You can create new versions that work better of MapReduce, like iterate MapReduce. You can decide I'm not going to use MapReduce. I'm just going to build my own apps over HDFS, Hadoop Distributed File System. For example, in practice, you know, I consult about half the time, and in practice, you know, and in consulting it's very simple. You either solve the problem or you don't get paid. If you don't get paid, your children don't eat. And it turns out I have teenagers and they eat a lot. So, you know, I'm highly motivated when I consult to solve a problem in the simplest possible way. So many times I solve the problem by taking Hadoop and just building very simple so-called stream-based or Hadoop streams over there and not using MapReduce because it's just much simpler. Now, if MapReduce works better, I'll use it, but you can build whatever app you want over HDFS, and that app can be designed so that it gives you exactly what you need for your domain of science. So you have that freedom, you just have to take advantage of that. Same thing over MapReduce. You can build whatever you want over MapReduce. So we got a stack, and you're allowed to attack anywhere you want in that stack. At the data, you could build a table service, etc. So this is so I'm not going to talk about it in this talk, because I'm going to eventually get to sector, but this is the stack you can't touch unless you're at Google. This is a stack you can touch, but you're probably touching in the wrong place. And this is what the stack looks like at Amazon. I'm not going to talk about it. I just want you to notice that this stack is different than this stack. So, you know, there's lots of different types of big data clouds. You could do whatever you want, but the programming style is quite different. This is sort of based more on asynchronous queues, etc. I'm going to talk for a little bit. I'm going to talk a little bit about NoSQL databases, probably pretty quickly. So NoSQL stands for not only SQL or NoSQL. It basically gives up some of the ACID properties that are traditional with databases. They usually support flexible schemas. Google's Bigtable, Amazon's S3, probably Facebook's Cassandra and Google's Bigtable are examples. You could think of these as distributed key value stores like S3 and Voldemort, column-based stores like HBase and Cassandra, and then they even have document and graph-based kinds of NoSQL systems. So why does this matter? These aren't my benchmarks, you know, if I have a distributed MySQL, say on 50 gigabytes of data, it might take 300 milliseconds to write and 350 milliseconds to read. In Cassandra, in the same way, I could reduce that dramatically. Now, it's conservation of difficulty. I don't have the ACID semantics that are required, but in scientific computing, we often don't need that. There is this sort of pseudo-theorem that's pretty, you might want to think about. It says if I think of consistency, availability, and partitions, as I do scale out, I can only get 2 of those 3. So most websites decide they're going to give up consistency and just have high availability, and that's more or less how the NoSQL database is started. And so if you don't have consistency, what you replace it by is what you might call eventual consistency. This is what S3 has. You basically use replicas, and that gives you durability, and that gives you availability. And if you ask, instead of everything being consistent, what you want is if there's no new data, then over some period of time, the data eventually becomes consistent. And that's sometimes called BASE, basically available soft state eventual consistency. Not a bad, you know, you had to get something that you would remember like ACID, so the community came up with BASE. Okay, why did you come from all over the world? You came to learn about sector. Gu's going to tell you really about it. I'm going to do this quickly, then give you Gu. So sector is designed to be like, it's internet scale data, internet scale computation, but it's distributed. So there are a couple ideas. One idea is you extend the stack downward to transport. So for people who've built these large data clouds, there's issues at the top of the racks. It's very difficult to communicate. Over the last long time, we've been working on algorithms, and the best is Gu's UDT, that allows you to move big data anywhere you want around the world. So just in the same way you can think of MapReduce as a GFS application, we think of the sector distributed file system as a UDD application. So we build over UDT, which is this protocol that you can move data. And then, so the first idea is you extend the stack downward. The second idea is you replace map and reduce with any UDF. So I could take any data in a storage in a data warehouse and apply UDF to it in a few lines. Gu's going to show you that in a little while. UDT has sort of been industrial strength for a while. It's been OEM'd. It's been used in, I think, 8 or 9 commercial products. It's been downloaded over 25,000 times. It's a non-TCP protocol. And in this area, there's no reason we have to use TCP. It's a non-TCP protocol. TCP is the, depending upon which version of it, it's sort of the purple, it's essentially the purple line. UDT has this, it's a so-called additive increase multiplicative decrease. It has a much different curve, so it's a non-TCP protocol. At a high level, UDT looks like Hadoop, but it has a couple main differences. It has multiple master nodes, servers, and everything's encrypted. It can be encrypted so that you can do things like work with HIPAA-compliant data and things like that. I have 2 slides that sort of explain some of the differences between Hadoop and sector. So the first, at 50,000 feet, it's similar to the Google Hadoop stack. Main differences, it uses a different non-TCP protocol just so that it could scale to distributed data centers and it could be a lot faster. And number 2, it sort of allows you to think that your basic unit is the user-defined function, and I can code that up over a data center. It does not try to build a file system. Building a file system is hard, and so it's an overlay over an existing file system. So most scientific data comes chunked as files. If it doesn't come chunked as files, it's easy to chunk it as a files. So Sector takes these files, fills a data center with them, and processes these files in parallel by the data center. So the programming model is both MapReduce and UDF. The protocol is UDT, not TCP. Hadoop writes replicas anytime it writes, which is fine for many applications, but for scientific computing, it's slower to write 3 replicas than it is to write 1. You can configure Sector so it behaves like Hadoop and writes 3 replicas. You could also configure it so it writes once and then there's a heartbeat, and a couple seconds later, whatever duration you want, it will make sure there are replicas out there. So that simple idea of using a heartbeat instead of always writing n copies can be very, very helpful sometimes. The security is built already in, because in biology we have to work with data that's secure, and it's written in C++, not Java. Speeding up, this is for people who want to, so this is helpful, this slide is helpful if you're trying to decide whether to use Hadoop or Sector. People who use Sector are usually happier. So if you want to be happy, I would use Sector. But there are more people using Hadoop. So if you want to have more friends, you could use